Thank you. Well, first of all, thanks to the organizers for the invitation to give this talk. And indeed, I'm going to stick to the curve space. And instead of talking about amplitudes, the idea is going to be to understand how to apply techniques that we know very well that work in flat space for amplitudes and how to use them to simplify our calculations in cosmology. So here I'm going to tell you about self-dual cosmological solutions and color kinematics duality, aka the double copy. And
should work now, sorry.
There we go. Perfect. Well, a very short motivation because, of course, everyone has been talking about this in this session. And it's the idea that cosmological correlators in general can be very complicated to compute. Instead of knowing many loop orders like we know for flat space scattering amplitudes, we know just one loop order in certain cases and not very high points. And these are things that are important for CMB in large scale structure, as Hayden mentioned earlier. So the idea here is how can we use techniques that we know from flat space, from scattering amplitudes that can help us now simplify this. And one of these techniques is the double copy, where we know how to square gauge theories and find gravitational solutions. So the big question that has been around for the past few years is, can this actually have a reasonable double copy? And in fact, it's known that you can, depending on how you want to do this, run into trouble already at 4.3 level. So instead of just trying to go ahead and do maybe one of the most complicated cases, here what I'm going to do in this talk is just go to the simplest case in flat space and generalize the simplest flat space case of a double copy to now cosmological spacetimes. So the cleanest double copy example in flat space is self-dual solutions. That means just that the Yang-Mills or your gravitational theory have a self-dual curvature, which in terms of coordinates here, you just see your field strength has to be self-dual, all your Riemann has to be self-dual. So these theories have a lot of very nice properties. So for example, if you consider on-shell scattering amplitudes with real momenta, all of them vanish, which just shows the fact that these are classically integrable theories. And furthermore, you can compute loop level amplitudes, and they're just exact at one loop. Everything else vanishes. So they are very simple theories, and they have a very nice double copy structure. And if you want to obtain the full theory now from these self-dual theories, you can do a perturbation around these self-dual solutions and obtain the full theory. So now let me go into details and show you a bit more of what are the nice properties of these self-dual solutions, both in Yang-Mills, in gravity. And I'll just show you how the double copy works there and how we can generalize this to more generic curve spacetimes. So this has been done many years ago. For example, these self-dual solutions were found in the 90s. And the nice properties arise when you look at this in light cone coordinates. So my metric is just going to be given like this in double light cone coordinates. And in what is called the light cone gauge, meaning that the U component of your gauge field is 0. Once you pick this and decide that you want to solve this self-dual equation, which immediately implies the Yang-Mills equations are also satisfied, what you find is that your gauge field can be expressed now in terms of a differential operator, so this capital pi here, which is just derivatives now in a subspace of your 4-dimensional space. So now we're going to be having just interactions in a 2-dimensional subspace, which is defined by these W and U coordinates. And it's just in terms of a simple colored scalar, this capital phi here, that lives into a joint representation. So for this to be actually a solution to Yang-Mills equations and self-dual equations like this, what you need is that this scalar field satisfies an equation of motion that is very simple. It has a standard kinetic term, and it just has 3-point interactions like this, which are just given by your standard Lie bracket. So this is just simplest case that you can have. And of course, a very well-known property in 4D is that this is going to be a scale invariant theory. So when I'm saying these equations hold in flat space, they also hold for any conformally flat metric, which is something that I'm going to be using later. Now, if you want to actually go to amplitudes, you can do so. Just do your standard perturbation theory. And for example, you can take this field to be a background solution that's non-trivial for your equations of motion, or use it as a generating functional. If you use it as a generating functional, you'd be computing fully off-shell amplitudes. If it's actually a non-trivial solution of your equation of motion, what you have is that these legs will be on-shell and just one leg would be off-shell. So you can just go ahead and do your standard perturbation theory, compute off-shell amplitudes, and you'll find that now these amplitudes are given as usual by your structure constants of your gauge group. But now there's another structure constant that arises that I'm going to be calling the kinematic structure constant. And it has the same properties as this structure constant. It satisfies Jacobi identities, but now it's given in terms of momenta of your legs that you're scattering. So here's where the color-kinematics duality comes in. They satisfy the same algebra, so you'll be allowed to exchange one for another to do the double copy in a little bit. So let's look now at the gravitational case. So it's very similar to the Yang-Mills case for self-dual gravity. It was actually done in the 70s, so a long time ago. And the idea, again, is work in light-cone coordinates, light-cone gauge, which sets one of these components to 0. And again, your field, which is going to be a perturbation, well, exact perturbation around Minkowski, can be written in terms of these differential operators and a scalar field. And this scalar field has to satisfy equations of motion, which again just have 3-point interactions. And instead of having a Lie bracket giving you the 3-point interactions, now you have a Poisson bracket, which is this Poisson bracket over here. And this is going to give you your kinematic algebra. So let me now just show you what's the idea of the double copy. So basically, you have your Yang-Mills theory now defined by this color order scalar satisfying these simple equations of motion. And this describes all the self-dual solutions for Yang-Mills and your self-dual gravitational theory. So if you want to do the double copy at the level of the equations of motion, you will just have to exchange this color scalar by a normal scalar and the Lie bracket by the Poisson bracket. If you want to do it at the level of the amplitudes, you have to exchange now the structure constants that, again, both satisfy Jacobi identities. And in fact, these structure constants have a geometrical meaning here. In this case, it's something very simple. They just area preserving diffeomorphisms. So they're the structure constants of this algebra. And we'll see how this will get deformed when you go to curved spacetimes. So this is a work that I've been doing now with Arthur Lipson and Silvia Nagy, and hopefully will come out soon. And the idea is now, again, you want to have self-dual solutions, but now in more generic curved spacetimes. So like before, we looked at the curvature that has to be self-dual. That curvature, you can think about it as actually being the Weyl tensor on shell. So here, if you consider this to be the Weyl tensor, of shell, you know it will be in scale invariant. But when you go on shell, meaning that you take the Ricci tensor and it has to satisfy Einstein equations, then now you'll have terms that depend on the stress energy tensor of your theory. So if you decide that this on-shell Weyl tensor has to satisfy this self-dual condition, by default, just this equation will give you the trace reverse Einstein equations and the Bianchi identities. So solving this is enough to have a self-dual solution of gravity. So the simplest case of this, of course, is de Sitter. So you can take this strategy and now go ahead and say, well, my stress energy tensor is just a cosmological constant. So this is what was done last year by Arthur and Silvia. And now, instead of considering a perturbation, well, exact perturbation around flat space, now you take a de Sitter spacetime. And your ansatz is going to be very similar. So your ansatz now gets deformed with having a time dependence. So this is going to be conformal time. So just like in Hayden's talk, this is going to be what he was referring to as eta. Now I'm calling it tau. And the differential operators now get slightly deformed, again, by this conformal time. So one of them will be the same differential operator that you had before in the flat space case, but it has to be symmetrized with another one that has a time dependence that comes from your de Sitter space. And very interestingly, this will be a solution to the self-dual equations as long as they satisfy this equation of motion, which is the equation of motion of a conformally coupled scalar in de Sitter space, again with 3-point interactions. But they're defined now with a new bracket that we can call a deformed Poisson bracket or a Jacobi bracket, which still satisfies Jacobi identities, but it has a deformed Leibniz rule. So this will give you a new kinematic algebra and different scalar constants that now are deformed by this tau. So very clearly, you can do a double copy in the same way in this case as you did in flat space. You just have to exchange now the Lie bracket by this deformed Lie bracket that depends now on the conformal time. And there's also going to be a structure constant that you can exchange for a deformed structure constant. So everything follows straightforward. So now the question is, of course, okay, these are maximally symmetric spacetimes. They were very simple. Can we do something more general? And can we do cosmology with it beyond just de Sitter? And the answer is going to be yes. So let me just very briefly introduce the FRW spacetimes that you already saw in the previous talk. So now you have this spacetime in conformal coordinates, so it's just conformally flat. And this factor in front is called the scale factor. It just depends arbitrarily on your conformal time. And we're going to now write this self-dual metric as an exact perturbation around FRW. So the ansatz is going to be, again, very similar to what you had in de Sitter, but now you're going to have the scale factor in front of here. And I'm going to just say I have two differential operators. They're linear in derivatives, and they can have some deformation in terms of some function that is a function of conformal time. And then I'm going to ask, like, what are the self-dual solutions? So in this case, the source is going to be a generic d mu nu. So for plane FRW spacetimes, these d mu nus can be thought of like homogeneous and isotropic, so it's just a perfect fluid. Here I'm going to be more general and just not assume anything about a perfect fluid and just work with viscous fluids. So we can go ahead and pick a specific viscous fluid, or we can go back and even ask a more general question, which is, what are the most generic conformal class of metrics that have self-dual Weyl tensors? And then we can understand which ones are physical. So if you just decide to impose that you have a conformally flat metric plus the perturbations, and that it has a self-dual Weyl tensor with these ansatz that I've been mentioning, what you'll find is that a solution indeed is given with this operator, again being the flat space case, and a deformed one, which is deformed by this, I'm going to call it the zeta auxiliary function. And this auxiliary function just has to satisfy a simple constraint, being that its derivative over sigma squared is constant. This gives you three different conformal classes of metrics that can have this self-dual off-shell Weyl tensor. And they're parameterized either by 1 over tau, which is going to be your de Sitter case, by a constant being 0, which is your flat space, aka no deformation, or by a constant that is non-zero, which actually is going to give rise to a new solution. And again, you can rewrite the equations of motion of these scalar fields such that they look like you have a scalar with a propagator that's just a conformally coupled scalar in FRW, and a three-point interaction, but now it's given in terms of this auxiliary variable over here. So remember, this is off-shell Weyl tensor, so it doesn't matter what the scale factor of the physical metric is. And this is just written in terms of an auxiliary FRW metric, which is determined by this auxiliary function. And generically now you have a Jacobi bracket that is the deformed Poisson bracket in terms of this auxiliary function. Still satisfies Jacobi relations, but doesn't satisfy Leibniz rules. So now we have our very simple cosmological self-dual double copy for these three classes of conformal metrics. So again, you can do field redefinitions in the Yang-Mills case just to write it as something that has the same propagators. So we can write it as a conformally coupled scalar field in FRW with this type of three-point interactions that depend on the scale factor. And in self-dual gravity, now I can rewrite the equation that I showed you before to actually have a propagator in the physical FRW metric. And the interactions now read this form. So this was just a field redefinition to massage this to look like what you would expect, like a perturbation around FRW and an interaction there. So you will see now that the double copy simply is determined by this auxiliary function zeta, that it can take, again, three values for the three different conformal classes. So, okay, so far we have this abstract version of a double copy for a class of three classes of conformal self-dual metrics. And there's not much physics yet. So now what I'm going to do is now analyze what these new solutions that are cosmological self-dual solutions actually mean. So to do that, I'm going to fix a bit more my spacetime. So far the freedom was I have a self-dual Weyl tensor but I left the freedom of like your Ricci scalar entirely free. Now I can pick that the Ricci scalar, in fact, is the same as the Ricci scalar of FRW, which will be similar to the case of what we did in flat space and de Sitter. So if you just require this additional, very simple constraint, which means that you only have now degrees of freedom in the traceless Ricci, now this auxiliary function now gets related to the scale factor of the actual physical metric and gives rise to 4 different solutions. And these 4, 2 of them were already known. So one was the flat space self-dual case. The other one was the de Sitter self-dual case. And now we get 2 new ones that perhaps you would expect them to happen. One is what we call radiation-dominated FRW spacetime. So in cosmology, we call it radiation-dominated because it has a traceless stress energy tensor. So it looks like the matter is just a gauge field, just radiation that's around. And in general, all the other components of the stress energy tensor are non-zero. The scale factor is linear in the conformal time, and the interactions just look like a 3-point interaction like this. Of course, we've been using a lot of scale invariance here, so it's not surprising that one of these nice solutions that appears tends to be the radiation solution, since this traceless stress energy tensor already hints at the scale invariance. But there's another solution, which is what in cosmology we call non-accelerating FRW. So this has a scale factor that in conformal time is an exponential. If you go back to what's called cosmic time and just change what your time coordinate is, this is linear in t, which means its second derivative is 0, so it's not accelerating. And the Ricci scalar behaves exactly like it's expected for these spacetimes. It has a non-zero t mu nu, and again, non-zero 3-point interaction. But the difference is this radiation is in the same conformal class as the flat space case. So it uses the interactions just like a Poisson bracket, not in the form as before with any time components. This non-accelerating case is in a different, it's the new class of metrics. And this Poisson bracket outside is depending on this constant that we call the Hubble constant in conformal time. So now it's deformed by this Hubble constant, and now you get a Jacobi bracket. So let me focus a bit more on these radiation solutions because they appear a lot. So I just told you that if you want to have this nice property that the Ricci scalar is the Ricci scalar of the corresponding FRW spacetime, then you just have this radiation that's conformal to the flat self-dual solution. In this case, the energy density behaves like 1/8⁴. That's the standard case for radiation in cosmology. Again, A being the scale factor in front of the metric. But you can also obtain radiation spacetimes, meaning spacetimes sourced by a traceless stress energy tensor from the other conformal classes. So the other conformal classes were the de Sitter self-dual and the non-accelerating self-dual. So in those cases, if the scale factor in front of your metric here, you set it to 1, but here this scalar field satisfies the equations of motion with the Jacobi brackets that are deformed, then you still get that the metrics are sourced by traceless stress energy tensors, but the energy density behaves in a way that's not standard for cosmology. So in this case, it's like 1/τ², not the standard case. Or in this case, it's just constant, but non-zero. Again, not the standard case. But it's just interesting, of course, since this has a lot of scale invariance hidden, that these radiation spacetimes arise not only in one of the conformal classes of metrics, but in the 3 of them. And as the last example, I'm just going to show you how to make generic self-dual cosmological solutions. So I gave you a specific class of spacetime that just has 4 different cases that have their Ricci scalar equals to the Ricci scalar of FRW. Now, if you allow for slight deviations of that, you can get any generic cosmological solution that you want. So now, again, I'm just going to have my metric defined like this, with this scalar just being any of the 3 conformal classes. And now I want to fix my scale factor to be a power law. So like it has been shown before, these are very interesting cases for cosmology. And what we find is that this will correspond indeed to spacetimes that are sourced by a viscous fluid. And their energy density indeed behaves like FRW, plus a differential operator that's time dependent and second derivative of W of phi. Now, the equation of state, which is the energy density, the pressure of the source over the energy density, also behaves like FRW, so this will be the FRW value, plus another differential operator in this function, which tells you that this looks a bit like what is cosmological perturbation theory for people that do cosmology, that if we have that this function is small, these solutions actually are very close to the solutions that we have in cosmology, where your metric actually feels the perturbations of whatever matter that is around. And instead of just being isotropic and homogeneous, you actually have perturbations. So this allows you to have a very generic spacetime that still has some hidden nice properties in terms of Poisson or Jacobi brackets. So just to conclude, I'm going to review how the double copy looks like for these special 4 cases that I showed you. So again, this will be either your flat space or your FRW Yang-Mills solution. They're the same. I'm just writing them with different phis with a field redefinition. And these are the equations of motion of those special 4 cases that I told you. Now, to do the double copy, you just have to do these replacements that I'm showing you here. And I'm just showing that there's 3 different ones because these are the 3 different conformal classes. Each conformal class has a different Poisson bracket or Jacobi bracket modified by time or by the Hubble constant. You can do the same for 3-point amplitudes. And now what you do is you go from your standard gauge theory structure constants now to kinematic structure constants that have now a scale factor involved in there and a deviation from the standard structure constants that also depends on time. So let me just finish with the future directions. So I showed you that in flat space, we have a very well understanding on the geometrical meaning of what the kinematic algebra is. It is not very clear how these deformations play a role and what do you have now as your actual kinematic algebra. And also, it's interesting to understand what the Moyal deformations are, which are just a deformation of the Poisson bracket that allows you to get chiral higher spins in flat space. And these theories also exist in ADS, so it would be interesting to understand if you can do the same with these new cases. Of course, we would like to understand now the simplicity in correlators. The double copy, in fact, for radiation spacetime has a very simple double copy in this case, so it seems even simpler than the de Sitter case, so that's an interesting thing to explore. Perturbations around self-dual solutions in curved space, if there's an integrability here, or if there are any other self-dual solutions even beyond cosmology. Thank you.
Thanks, Mariana, for a very nice talk. So let's see if there's any questions. There's one question here.
Do you know if the formulation in terms of the self-dual Einstein condition in terms of the scalar field phi, is it related to the, so there's a slightly older formulation of the same condition by Przjanowski
Yes.
from 80s or
Yes.
whenever. Is it related by gauge transformation? Like type D to type N or something?
I haven't checked in the curve space if it looks similar, but you probably can do a gauge transformation along the lines of the flat space case to get a formulation like that, and that allows you to write the scalar case in like a nonlinear sigma model. So my guess is yes, there should be something similar, but again, with these deformations, it's not entirely clear, so it's something to check.
Right, maybe I can ask a question while other people think about it. So you introduced several modified brackets, Lie brackets, or Poisson brackets in the gravity situation. I wonder if you actually undo that and go back to gauge theory, would they have a meaning, these modified brackets in the gauge theory?
Yes. This is something that we started thinking about because we're doing, in a sense, this kind of double copy is a double copy on a fixed curve background. So on doing that, maybe gives you more like you also double copy the background case, but I don't know the answer. Yeah.
Any more questions? maybe the, oh, there, I could, there was too many people there.
Can you comment a bit more as to why double copy seems to be easier in radiation than in the jitter?
Yes, well, radiation you can think of, radiation-dominated spacetime, and FRW, you can think about it as like half a Minkowski space just with a boundary. And it's kind of, you can think of just like propagation on Minkowski, and then you just put a time boundary in the middle, and it just makes things easier. There's also a sense of scale invariance, which is because the source is a traceless stress energy tensor. So it just simplifies the calculations. Yeah.
Okay, thank you so much.
All right, I think we're already into the lunch, so we should probably end there, and let's thank Mariana.